Here's practice exam 2. Okay, so these ones you only need to give an answer. I'm gonna do more than just give an answer just because I want this to be helpful. Okay, so I need a function from the integers to the integers that is injective but not surjective. Okay, so let's see. So injective, I could do like a line, just not a flat line, not a line of slope 0, but any other slope should be fine. But I don't want it to be surjective, so maybe I want something that like skips a point, you know? So maybe I do like f of x is x plus 1 for all integers that are greater than or equal to 0. And then is x less than 0. So then f of 0 is 1, and f of -1 is -1. So I skipped 0 there, but every other number gets hit. So this is injective and not surjective. Okay. Plenty of other examples that you could have come up with. Totally fine. And you don't need to justify, but I'm just doing that just to sort of help us see what's happening. Okay, so H goes from the reals to the reals, and this is its definition. We get to just assume it's bijective. Okay, and so now because it's bijective, we can define the inverse, right? So this one's not too bad about the domain and codomain because remember your inverse's domain is your original function's codomain. Okay, so like you could think of it like this one goes here, right? And this one goes here. Okay. But of course we can see here that each of their domain and codomain are the same. So it's not really that huge of a deal. Okay. So now we just need to figure out what's the assignment rule. And there's a lot of different ways you could do it, but we could do this thing that maybe you learned in calculus where you take like you take this, right? And then you just flip-flop the x and the y, and then you solve for y. So let's see. So I add 3 onto the other side, so x plus 3 equals 2y to the 5th. So I fifth root both sides. And remember, this is okay because this is an odd root. So I don't need to do the plus or minus business because it's an odd, because 5 is an odd number. And I divide both sides by 2. So I get y equals the 5th root of x plus 3, all divided by 2. Great. Okay, so then that means that h inverse of x is going to be 5, sorry, the 5th root, that looks like 5 times. The 5th root, there we go, of x plus 3 over 2. Yay, okay, so, oopsie. Okay, so now we have these index unions and intersections. So, you know that I like to draw out sort of the first couple of them. So who are our main characters? Well, certainly 1 and 7. And then when n is 1, it's going to be 1 minus 1. So that would be 0. So that's another main character we have here. And then 7 minus 1, that's 6. So I should probably give myself a bit more room. Okay, so, okay. So these are my main characters. So, maybe my A1 is I go from 0 open bracket all the way to 6 closed bracket. Oops, pretend like that's actually hitting 6. A2 goes from 1/2 to 6.5. And you could keep going. A3 is what, 3/4? Wait, 2/3? Not drawn to scale. And then 6 2/3, etc., etc. Not drawn to scale. Okay, so all these things union together Well, here you can see I almost hit 0. Okay, but I don't actually touch 0. All my, only A1 has that, but I'm unioning these together, right? So I get to include all of them. And then as you can see, as n gets bigger and bigger and bigger, I get closer and closer to 7, but I never actually touch 7. Okay. So I almost get to 7, but not quite. Okay, so it's 0 to 7, both open brackets. Okay. And then the intersection, let's think about that. Well, the intersection as n increases over here on the left here. I think I have little, there we go. Over here, right? As n gets closer, gets bigger and bigger and bigger, I get closer to 1. And every single one of my sets includes 1, because every single one of my sets starts a bit to the left of 1. So they all have 1 in them. Okay. And then on the right-hand side, as n increases, we keep getting bigger and bigger, but remember we're doing the intersection. So really it's just this one, right? It's the first one, it's the 6. And all of them have 6 because A1 has 6 in it, and then all the other ones have 6 in it. So this is close bracket 1 to 6. Okay, and again, you don't need to do all this explanation. This is just me explaining it right here. So now I have this weird collection of sets. Okay, so if I union all these together, then I get all like 1 over x such that x is in the integers besides 0. That's one way to explain it. There's tons of other ways you could explain it, but you can see I get like 1 and -1, 1/2 and -1/2, 1/3 and -1/3, et cetera, et cetera. Okay, but of course I can't divide by 0, so. But then the intersection of all of these, well, actually none of them have anything in common. You can actually consider just like B1 intersect B2, right? Which is 1 and -1 intersected with 1/2 and -1/2, and that's the empty set already. So any other sets intersected with the empty set is always going to be the empty set. So, so that's what we get there. Give an example of the following. You do not need to prove any of these. Okay, but I do say that you need to give like a short explanation or something for some of that, for both of them. So can a bounded sequence of real numbers not converge? This is true. Answer is yes. For example, sine of n for n in the naturals, right? Because remember, sine just forever and always just does that. I know that's for the real numbers, but it's even more all over the place for natural numbers, right? So it never converges to anything, but it is bounded because between every single part is between and including 1 and -1. Okay, so great. Can an increasing sequence converge? Yes. Let's see. So you need to be increasing, but you can't go to infinity. So like, what if I just kept getting closer and closer to 5? Right? So what if I had like 5 minus 1 over n? Right? Because as n gets bigger, we get closer and closer to 5, we get bigger and bigger. Right? Because we start at 4, and then we have 4.5, and then 4 and 4 2/3, and so on and so forth. We keep getting bigger and bigger, but we just get closer and closer to 5. Can a decreasing sequence diverge? Yes. Because remember, you could diverge to negative infinity. So, alright, so just take the negative natural, well, take the naturals and negate them. Okay. Let P be a prime number. Does there exist any natural number such that GCD of P and A is not one? And so remember when I talk about here, I don't mean 0. I mean something like some positive integer. Okay. Well, remember in general, like, so like let's think about like GCD of 3. Right, so if I do 3 and 2 or anything like that, like 3 and of course with 1 it's going to be 1, but if I did like 7 or something, that'd be 1. But you know, the trap that you could fall into is thinking that 3 has to be like, it has to be something that divides into 3, right? Or like, but you could do like here where 7 is bigger, but you could do like GCD of 3 and 9. I don't know why that took me a second to think of that one, but but these two, their GCD, their greatest common divisor is 3 itself. Okay. So, okay. I mean, you could do 21, you could do a whole bunch of different numbers, 12. And 3 famously is not 1. So the answer is yes. Consider GCD of 3 and 9, or GCD of P and P squared, or P to any power, right? You could even have P comma P. Their greatest common divisor is itself again. So this is possible for sure. Okay, on to the next. Let f from the naturals to naturals be the function defined via the assignment, this thing. I meant to change this to and the definition of surjective function. Okay, so 1, so definitions. Let f from x to y be a function. F is injective if for all x1 and x2 inside of its domain, the following is true. So if f of x1 equals f of x2, then x1 must equal x2. And so remember, we talked about this. There's other equivalent ways to talk about the definition, and those are fine to list as well. Okay, so 2. And I know I'm not doing good English here. I probably should, but I'm feeling a bit lazy. Surjective. If for all y in its codomain, there exists an x in its domain such that f of x equals y. Boom, roasted. Okay, so part 2 is proving that f is not injective. Okay, so not injective means I just need to find a case where this fails, right? And remember, the negation of an if then is an and statement. So I need to find a case where f of x1 equals f of x2, but x1 does not equal x2. Okay, so I want to show a case where this is true, but this is not true. Okay, so for example, who could I, when I plug in 1, I would get 3 plus 1, which is 4. So f of 1 equals 3 times 1 plus 1 equals 4, because 1 is odd. And how could I get 4 from the other one? Well, I could plug in 8. And f8 equals 8 divided by 2, which is 4, because 8 even. So f of 1 equals f of 8, but 1 does not equal 8 famously. Therefore, f not injective. Yay. Okay, so now to prove that it is surjective, 1, 2, 3. So to be surjective, I gotta pick somebody in general in my codomain. So consider some, maybe we could call it Y. I don't know. And here I'm just specifying it because I think that makes it look nicer, but you don't have to do that. Consider Y in my codomain, and this is kind of where I immediately go over to Scratch. And I say, okay, I want f of some x to equal y. Well, you know what I could do? I could split it up into cases and stuff, but I feel like there's going to be a way that we can always get this. So if x even x over 2 needs to equal y, so x needs to equal 2y. Oh, would you look at that? So that'll always work. Okay, so consider, maybe I should have just said let before. I don't know, this just, it's not really that big of a deal. Let y be there. Consider 2y, which is still in the naturals, right? Because I can multiply a natural by 2 and still get a natural. Then 2y even, by definition or whatever. So f of 2y equals 2y divided by 2, which is y. Therefore, f is surjective. Right? Because some evil scientist comes up to you and says, hey, I bet you can't hit this natural number. And you could say, well, all I have to do is feed my function 2 times whatever that natural number is. And I do get that natural number. I do hit that natural number. All right. On to the next. Let an be this. The idea was n gets humongous, right? It doesn't really, and you don't have to write this part. I'm just doing this to be extra, I guess. I don't know. As n gets humongous, right, you have 2 times that, so that's going to be an even more humongous number. Who cares about this +1, right? Like these rich people, like the super famous rich people, it doesn't matter if you hand them $1. That's not really going to change. That's not moving the needle, right, on their net worth. So really what it comes down to is just n is the limit of n over 2n, which is just 1/2. Or you can do the L'Hopital's rule, because you get infinity over infinity is what the limit is. So you could take the derivative of the top and the bottom. Derivative of the top is 1. Derivative with respect to n here. And derivative of the bottom is 2. So, you can review, I believe you cover this in Calc 1. I did teach Calc 1 last. Ooh, you don't cover it in 224 though, I don't think. I think we talk about this stuff, but I don't think you cover L'Hopital's rule in Calc 1, part 1, like the 224 thing. But anyway, you all have taken Calc 1, so both sequences, so hopefully you know how to do this. If not, you can review some stuff. Or you can go with like this idea, like, oh, the one's not really changing stuff. So you get to sort of do that. You don't have to show this work. You could have just said 1/2 and you would have gotten full points on this. Part A, at least. Okay, so I want you to use the definition of convergence. That means do not show me L'Hopital's rule for part B. You will not get probably any credit. I want the definition, so the epsilon stuff, the epsilon business. So choose some epsilon greater than 0. And let L equal 1/2. This L part is more of a style thing. I just like how it ends up looking at the end, so I do this. And so I immediately go over into Scratch. And I say to myself, well, what is it that I want to end up with? I want to end up with AN minus L is less than epsilon. Right? That's sort of the goal for all of this. And so who is this character on the left? Well, this character is n over 2n plus 1 minus 1/2. Okay. But in order to talk about this thing, we're going to want to give them common denominators. So what do we get? So we get 2n minus 2n minus 1, because you got to remember to distribute the negative, times, over 4n plus 2. Did I do that right? I believe so. Yes, ma'am. Okay, so what do I get? I get -1 over 4n plus 2. And so remember, n is a natural number, so n is always positive. Okay, so this is a negative, so I just change the negative into positive. And so I want this to be less than epsilon. This is what I want, right? Okay, well, I can do some cross multiplication stuff. So cross multiplication. And epsilon is greater than 0, so I don't have to worry about, oh, that looks like I'm crossing it out. I don't want to do that. Okay. Doing cross multiplication, I don't need to worry that I'm multiplying by something negative. I don't have to worry about dividing by 0, because I just not. So, cross multiplication is not really the right word for this, is it? I want to divide by epsilon on both sides, and I want to multiply by 4n plus 2 on both sides. That's what I'm trying to get at. So 1 over epsilon is now less than 4n plus 2. And once again, I don't need to worry about switching this thing because everybody's positive. That sounds like a nice world to live in. Okay, -2 on both sides. Divide by 4 on both sides. Oh my God. There's a different way I did this last time. I don't think so. Oh, I could have made my life a bit easier. So I'm going to rewind. I'm going to, no, let's just do it like this. Let's just do it like this because, so how could I have made this easier on myself? I could have gotten rid of that too. I could have said 1 over 4n plus 2 is less than 1 over 4n, which is a true statement because I've made my denominator smaller, which makes my whole thing bigger, right? Like 1/2 is bigger than 1/3 is bigger than 1/4, etc. But I'm just gonna we can just keep going with this though. Let's just find a common denominator. So who do I get? I just need to multiply this by 2 epsilon over 2 epsilon. Okay, to get my common denominator. So I get 1 minus 2 epsilon over 4 epsilon, whatever that is. So this thing is less than n. That's what we want. So since epsilon is a real number, then by AP, well, we don't need to write that. Let's just do by AP. by AP, we can choose and n in the naturals such that 1 minus 2 epsilon over 4 epsilon is less than capital N. Then our absolute value of A sub capital N minus L is equal to 1 over 4 capital N plus 2 by scratch. And then we literally manufactured this N so that this whole thing would be less than epsilon. So what's the idea here? The idea is that I can replace N with this big thing, right? Because it's something smaller. And so when you plug in something smaller into your denominator, you get something that's bigger. And then we can go through this whole thing, right? So we can say, okay, I have 1 minus 2 epsilon over epsilon plus 2, but I can rewrite that as 1 over epsilon minus 2 plus 2. So this is just 1 over epsilon, which is just epsilon. Okay. Consider any n in the naturals such that n is greater than or equal to capital N, then A sub n minus L is equal to 1 over 4 n plus 2. But this, because n is capital N is smaller than or equal to little n, this is less than or equal to 1 over 4 capital N plus 2, but we just showed that's less than epsilon. Therefore, for any epsilon greater than 0, there exists a natural number such that for all n in the naturals, for all n in the naturals such that n is greater than or equal to n, therefore the limit as n approaches infinity of an is L, which is 1/2, right? Yeah. So don't forget to write in the definition of of convergence, of a convergence sequence. Okay. Okay, so that was kind of crazy, so let's go over it again. So how does a convergence argument go? Well, you first choose some epsilon greater than 0. You also need to know who your limit is, right? And then I go over into Scratch. And I'm assuming here what I'm trying to prove, but I'm allowed to do that because I'm in Scratch, right? So then I kind of figure out what's this number, what's this weirdo number that has to do with epsilon? If it doesn't have to do with epsilon, then it's not correct, okay? Sometimes people accidentally get too big too fast because they do all these fancy tricks, and the tricks might be true, but then you get too big too fast, and then all of a sudden it's like I don't know, you're not dependent on epsilon anymore. Okay, so I just need some n that's strictly bigger than this, right? Than this weirdo thing. But the Archimedean property, so that's where the Archimedean property comes in, right? So we use Archimedean property to choose somebody that is bigger than this, right? And then I say, okay, well, let's consider the absolute value of a with using this capital N, this new capital N, minus our limit. Okay, and so by our scratch, we can skip some of our parts here. And then, okay, well, if I plug in something smaller into my denominator, that gives me a whole number that's bigger, right? Because 1/2 is bigger than 1/3 is bigger than 1/4. Okay. And so then I do some movie magic and I get to epsilon. Right? So now I have epsilon is greater than or equal to this thing, right? Well, now I just need to say, okay, choose for any natural number that's bigger than or equal to this capital N. Now I consider this thing, because remember, this is from our definition. We need our definition to have somebody that looks like this. Oops. And so then I do all this stuff, and I say, okay, well, this is this by scratch. And then it's less than or equal to this thing, right? Because capital N is smaller than or equal to little n. And then we showed up here that epsilon is strictly greater than this thing, right? So that's what gives us this. And so then I state the definition of convergence. And then I say my conclusion. Okay. On to the next. Using the division lemma, prove that if n is in the integers, then 4 does not divide n squared plus n plus 1. Okay. What is the division lemma? For any n in the integers, there exists unique q's and r's in the integers for r needs to be greater than or equal to 0 and less than k, such that n equals q times k plus r. Okay, so the idea here is that, oops, this is what we're dividing n by. This is how many times k goes into there, and then this is the remainder. Right? So like 5 can be written as q times 2 plus r. Here my q would be 2, and my r would be 1. And I can't have q be 0 and r be 5 because r has to be between 0 and 2. Okay. Okay. So that's just a brief reminder. So here our k is going to be 4. Okay, so let's start our proof. By the division lemma, there exists unique q and r integers such that r is between 0 and who's the character we're trying to divide by? It's 4. Okay, so 4 is our k here. Okay, Okay, so, excuse me. And n equals 2 times 4 plus r. There are 4 cases. One, where r equals 0. Right, so n equals, I don't know why I'm writing it like that, 4q. 2, r equals 1. So n equals 4q plus 1. 3, r equals 2. Excuse me. So n equals 4q plus 2. And last but not least, r equals 3. Consider n squared plus n plus 1 for n equals 4q plus r. Okay, so I'm like not assuming who r is. We get yeah, let's do for 4 is that thing, for n is that thing. We get n squared plus n plus 1 equals what do we get? 16q squared plus 8qr plus r squared plus 4q plus r plus 1. Wow, there are no like terms. That's kind of crazy. Okay. In our cases, I don't know, there's plenty of other better ways to arrange this. N squared plus n plus 1 is, okay, so if r is 0, we just get 16q squared plus 0 plus 0 plus 4q plus 0 plus 1. So we could pull a 4 out of that first part. So this is 1 mod 4. So weird looking one. Let's change that. Okay, for case 2, r is 1. Okay, so I get 16q squared plus 8q plus 1 plus 4q plus 1 plus 1. So I get so equivalent to 3 mod 4, right? Because this divisible by 4, divisible by 4, divisible by 4. 3, r is 2. 16q squared plus 16q plus 4 plus 4q plus 2 plus 1. So that's 3 again. Because divisible by 4, divisible by 4. Okay. So if it's 3, oh, I guess I could have taken a 4 out of a lot of that. Whatever. Because really it just reduces down to what r squared plus r plus 1 ends up being, but we're already this deep in. Whatever 8 times 3 is, I don't know. So what is that? So we get 9 plus 1 plus 3. That's 12 plus 1, and 12 is divisible by 4, so we get 1 mod 4. We can see. Did I write really big at the beginning? Yeah. Oh, right. And I wrote the division lemma. You don't have to write the division lemma. You do have to reference it. Like this part you have to do, right? But this part you don't have to do, which is helpful. Okay. We can see that for all scenarios, 4 never divides. N squared plus n plus 1. Therefore, for all n in the integers, 4 does not divide n squared plus n plus 1. Yeehaw. Okay. Because if you're divisible by 4, right, what does that mean? That means you can be written as 4 times some integer, like q. But if your division lemma, if you're 0 mod 4, right, that means you can be written as 4 times some integer. So that's why they agree. Okay, now I want to prove this set inclusion. I'm going to call this set A. To prove, oh, sorry, not inclusion, equality. To prove that 2 sets are equal, I want to show inclusion both ways. So let's say I want to show A is included into 1 to infinity. Choose some x in A. Then there exists an n in the naturals such that x is in capital N plus 1. Right? Because if I'm in a union of stuff, that means I have to at least be in one of them. I could be in multiple of them, but I just need to at least be in one of them. What does it mean to be in this interval? That means that x is less than or equal to, is greater than or equal to n and less than or equal to n plus 1. Since n is a natural number, then 0 is less than n, and, oh, sorry, not 0, 1. My bad. I mean, that's still true, but it's not very helpful, right? I'm trying to show I'm in this thing. Whoop! Oh my gosh. Sorry, I almost lost my pen. And n plus 1 is certainly less than infinity. Okay. So, oh my gosh, I keep trying to write 0. I don't know why. 0 less than n less than or equal to, oh, less than or equal to, sorry. Okay, so let me draw attention to the mistake that I made. So I had originally said n strictly greater than 1, but that's not true because n could be 1. So it needs to be greater than or equal to 1. Sorry, it's my bad. Okay. This is still true. Okay, x less than or equal to n plus 1, less than infinity. So 1's less than or equal to x is less than infinity. So x is in this set. And make sure it's more clear that this is an inclusion of 1. Therefore, A is a subset of this interval. Okay, now I got to show the other way. You can use the same variable, you could use a different variable, whatever you want to do. It's fine. Then x is between 1 and infinity, including 1. Okay, so x has to be between 1 and infinity, and there's a bunch of different ways we could do this, right? But what we can do is we can think of like, okay, what is the floor of x? So consider this is a function that's well defined on real numbers. And define this to be capital N. Capital N is less than or equal to X. Right, because it could be that X is N, right? But N has to be less than or equal to X. If X is greater than N plus 1, then the floor of X cannot be less than N plus 1. And N plus 1 is strictly greater than N. So X is less than or equal to N plus 1. Actually, it can't be equal to N plus 1 because then the floor would be N plus 1. But that doesn't matter. So N is less than or equal to X, so that's equal to N plus 1. Sorry, and this has to be in the naturals because X is greater than or equal to 1. Okay. Therefore, X is in N to N plus 1. So X is in A. Therefore, and now I've used therefore like 4 times in a row. A equals 1 to infinity. And so I will say this one did take a bit of a trick here. Oh yeah, I'll just box it off. This one did take a bit of a trick here using the floor function. I mean, there's other ways you can go about it for sure. I think by way of contradiction could be good. That would be a nice one. There's a lot of different ways you could do it, but I will just say that to me, I think the one that I have for your actual exam is simpler than this one. So so if this really threw you off, this or doing it by way of contradiction or something really threw you off, I'm sure there's other ways that you could do it as well. That's it. That concludes this practice exam. Good luck studying. Happy studying. Of course, feel free to email me with questions and etc.